Let's talk about electron configuration in atoms. This is section 2 of your book. This will be 2 parts. So, what makes the electron configuration of an atom stable? Energy and stability play an important role in determining how electrons are going to act, how they're going to be configured in an atom. So we're going to come back to this question in a minute, probably in the next video. The ways in which electrons are arranged in various orbitals around the nuclei of an atom is called an electron configuration. We have 3 rules for writing electron configurations. And what are those rules? You'll want to stop on this slide and make sure you write them down, leave space so that you can define each one and give examples. So the Aufbau principle, the Pauli exclusion principle, and Hund's rule. So, according to the Aufbau principle, electrons occupy orbitals of lowest energy first. Aufbau is just German meaning filling up, and so you start at the bottom and work your way up. The Pauli exclusion principle says that atomic orbitals may describe at most 2 electrons. And to occupy the same orbital, 2 electrons must have opposite spins. So one would spin clockwise and one would spin counterclockwise. And that allows them to pair because it creates a magnetic field. And those magnetic poles would be at opposite ends, so they'd be able to attract each other, even though they're negative, both of them, both electrons. Spin is a quantum mechanical property of an electron. And as I just said, clockwise and counterclockwise. We use the up arrow to denote clockwise and the down arrow to denote counterclockwise. So an orbital is usually denoted as either a line or a little box like you see here. And for 2 electrons to go in that box, arrows have to point in opposite directions. By convention, we also write the first arrow going up and the second arrow goes down. Hund's rule. According to Hund's rule, electrons may occupy orbitals of the same energy, and this says in a way to make the spin direction the same. Another way of saying, since we're always going to put them up first, is to make them unpaired as long as possible. It's kind of like brothers or sisters. If you have an extra bedroom, you typically don't share. So, if we have 3 electrons, we would have them all going up. They would be in equal energy levels since these boxes are the same, are right next to each other. And before when I put the third one in, I wouldn't pair, I'd put it in its own box. Then when I add the 4th electron, now there is no option but to pair, and so I have to have opposite spins. So here's a diagram that would completely describe the periodic table of all the elements, both man-made and naturally occurring. And you see the arrow on the left side is showing that energy is increasing. So this electron box down here at the very bottom, this orbital box is the lowest energy, and these 6p would be the highest energy. Each box can hold 2 electrons. And so if you count them all up, you get enough that we could describe the entire periodic table. They don't have the 6F in there, so maybe not the entire... Oh, we needed to go to 7. Sorry, this doesn't have the entire periodic table. The Aufbau diagram shows the relative energy levels of the various atomic orbitals. Orbitals of greater energy are higher on the diagram. The range of electron energy levels within the principal energy level can overlap, and that makes it really messy to start talking about things, because if you notice here, we go 1s and 2s and 2p are higher, then 3s is higher, and then 3p is higher, but then 4s and 3d are really close in energy. And so we typically do the 4s, and then we do the 3d, and then we do the 4p. It gets even more complicated when we get on to the F orbitals. And I'm going to give you an easy way of determining what the order of filling is so that you don't have to straight up memorize it. So here is an example of oxygen. It has a total of 8 electrons. The first 2 go into the 1s, the next 2 go into the 2s, and then the next 4 are going to go into the p. And you'll notice it says px, py, and pz, and we have 3 boxes, and we'll go up, 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 and then the next one comes down. So here we didn't have to pair any in nitrogen, but then we do have to pair them in oxygen. In each element, the atomic number increases by 1, and so does the number of electrons, because remember we learned that each last chapter, the number of protons is equal to the number of electrons. So if I know the atomic number, I know the number of electrons. And electrons are really what do the work of chemical reactions. So the 1s orbital has 2 electrons of opposite spin. Then we have the 2s orbitals also has 2 electrons of opposite spin. And then the 2p orbitals, we have 3 electrons. We put 1 each going up, and then that 4th one comes back to the very first one and pairs it up. So here's a diagram I was telling you that will make it much easier for you. This is the entire periodic table. You'll want to write this down. It says 1s2, and so I'll demonstrate this in class for you today. And so we fill them up. A convenient shorthand method for showing electron configuration in an atom involves writing energy levels and the symbol for every energy level by an electron. You indicate the number of electrons that are occupying that by a superscript. And so that's what the superscripts up here are, is how many electrons can go in there. And the S can hold 2, the P can hold 6. You should be writing this down. The D can hold 10, and the F can hold 14. This would completely describe the periodic table. I am going to stop here. We will talk about it a little bit in class, but mostly I'm going to try and answer your questions. You should be getting the majority of the content here, and then I will clear up any misunderstandings in class. Thanks for watching. I'll see you in class.